are going to stream this session. There will be streaming in this session. So that's the opening. Yes, for the world. For the entire universe.
Beware of what we say.
¿Ya? ¿Estamos? ¿De empezar la transmisión? ¿Ya empezó?
Sí, estamos.
¿Estamos al aire?
Estamos al aire.
Ah, okay. Well, okay, thank you everyone for coming. This is the opening session of the conference Words of Entanglement 2019. This is the second version of this conference. The first one was in Brussels in 2017. And following the initiative and the energy and like the good vibe that was created in this first conference, we were able to make a second version in the other side of the world, that means here in Chile. So, well, I want to thank all the speakers, attendants, and also the team of this institute, which is the Institute of Philosophy of Complexity Sciences, for working hard with your respective parts to get this thing done. And I will tell you very short introduction of the Institute and some, let's say, logistic aspects that we have to be aware of during the conference. So this Institute, it's let's say, self-driven and self-organized institute. It does not belong to any government agency, no university, no corporation. It's not owned by anyone but us. So it's a sort of autonomous institute in that sense. It has been running for almost 12 years so far, and we sustain ourselves teaching courses in philosophy of science and other branches of, let's say, science, like biology or mathematical modeling. Well, now we are opening the data science and also quantum theory. So our, let's say, business model is to captivate people who don't want to belong to a university because they work or something and they want to learn still. So this is, or younger people that have no access, or anybody who cannot follow the common track can come here. That's basically the concept. And we have different people from different age groups coming here, working, collaborating, creating projects, and it's a sort of platform for intellectual development. So, and this conference is part of that, so thank you everyone for coming. Now I will explain some of the logistics of the conference. First, the most important, Wi-Fi access is given here. So that symbol is 0. And the name of that person is an interesting poet and singer from Chile that I recommend you to check on YouTube. Anyways, you will hear of her tonight, because at the dinner there will be some of her music played. So, coming to the social dinner, the reference for the map, in case you're going by metro, is Metro Station Manuel Montt. And I will show, can I move it from here?
Mm-hmm.
Yes. I will show the venue. So, no, it's not the venue, it's the social. So on the social you can see the address of the place and the name of the place, which you can also check on Facebook in case you have any doubt. So that's the place, and that's the price that has to be paid in there. Because it's a restaurant, so it's all set there, but we have to meet there. It starts at 7:30, 7:30 Chilean time, means 8-ish. Okay, so coming to the schedule, as any other conference, it will have some changes on the schedule, last minute changes. And the first change I'm aware of is that you have to switch the first and last talks of tomorrow. That will imply some change times accordingly. The coffee breaks will move, because the first talk was supposed to last for an hour, now it will last for 45 minutes. So there will be a little accommodation with the timing, but it's nothing too strong. Concerning the lunch, at the lunchtime, we are going to go to the restaurant here at the corner, the Peruvian restaurant, and we will have the menu options available later, because they will give it to us around 11:30 a.m. We will know what the options are. For non-vegetarians, because vegetarians have no choice, they will eat the vegetarian dish, which is a vegetarian dish with no explanations, unfortunately. So, non-vegetarian people will have the choice to choose between 2 or 3 salad options and 2 main courses. And also the lunch includes like a soft drink, Coca-Cola, Fanta, Sprite, something like that. Last but not least, the talks have to be sent to this email address, acastilo@ific.cl. Please, whenever you're ready with your talk, send it to this email address. So Angela will prepare the talk to be presented here. You cannot use your own laptop to present the talk because we have our recording system settled in this computer. So, not your own laptop, send the talk. Now, if you don't want to send an email, we have a USB stick available at the reception, so you can put your laptop and we will take care of it with the USB stick. Of course, in case of any question, you can ask me or ask in the reception, but better to ask me. And also, I think you all have registered already, so nothing concerning registration. If you need a receipt or anything like that, please explain or talk to the counter people. They will prepare receipts for you for reimbursement and so on. So after this logistic aspect and after the explanation of what we are and what we do, we finally can come to the conference. So, program. You know the program already, you all have it in your hand. So now we start with the keynote talk, which is starting slightly late, but please, you have an hour for it, so don't worry. I guess 50 minutes plus 10-minute questions. And I will be the chair of this session, which is, I'm already here. And I will kindly get close to you and invite you to chair sessions along the conference. So for the moment, we start with the keynote talk, quantum measurements in a contextual and realistic framework by Professor Philippe Grangier, which, by the way, and with this I finish, taught at the last part of a course in quantum logic that we hosted the last 2 days on the Tuesday and Wednesday. Professor Carl Bossing started the course, give us a whole introduction about the logical and mathematical and philosophical aspects of quantum logic. And then we had the, let's say, the complementary historical and experimental account of the entanglement, let's say another quantum properties by Professor Philippe Grangier. So actually, I want to thank you both here for the work, because it was a great course. People were very happy, and we are all satisfied. We will prepare edit the recordings and so on. So it was really good that you made this for us. So, well, nothing else. Please welcome Professor Philippe Grangier. Thank you very much, Professor.
Okay, so yeah, it's working. So good morning, everybody. It's a pleasure to be here. Thank you, Thomas, for organizing all the session and all these things. So I will speak about some work we are doing with a colleague, Alexia Auffeves, who is a young woman working in Grenoble, mostly doing quantum thermodynamics. But both of us have other activities at Quantum Foundations, but we work together on Quantum Foundations. This work, which was, there were several papers in several journals recently. So it will not really fit with the title, but we will try to get an idea of what we try to do. So it's basically the idea related to entanglement, obviously, Einstein, Bohr, Bell, and experiments. So you know these experiments have been very successful and are basically concluded. And our question is what kind of philosophical implication about quantum mechanics can we deduce about that? And this, so what can we tell about quantum states, about reality, objectivity, and all these things? This talk is about that. So we all know Einstein, who was a founding father, clearly, of quantum physics. He is very famous for introducing the Licht quantum, quanta of light, which became photons into 1905. He is also very famous that he never really liked quantum mechanics. So there was this very famous paper, also in 1935, with Einstein, Podolsky, and Rosen. They proposed the definition of physical reality, of elements of physical reality, and from that they concluded that quantum formalism is incomplete. There are some hidden things which should be that we should know, but formalism forbids that we know these things, which are called hidden variables now, but in their terms it was an incomplete formalism. So this was a very long debate with a long discussion between Einstein and Bohr. Bohr disagreed. Bohr really thinks that the quantum formalism is complete. Then quantum mechanics was very successful, so this turned into philosophy rather than physics. But as you know, in 1964, John Bell introduced his Bell theorem, which allowed to experimentally check these ideas. So there were many experiments done about Bell's inequalities, first in the 70s in the US, then we did some in Marseille, in France. So I was a PhD student at that time working on this experiment, which were initiated by Jan Aspe, and which introduced also check of relativistic separation with very fast switching of the measurement of the experiment. Still, it was not perfect, so during about 35 years, there were many other experiments, and then finally, in 2015, we reached a final conclusion that is all defects, potential defects of this experiment were fixed. And so this is a paper by Jan Aspe in Vrije, closing the door of Einstein and Bohr's quantum debate. So the experiments are as good as they can be, and the conclusion is that quantum mechanics is correct, and that EPR ideas and Bell's hypothesis, which are more or less the same, it's called local realism, doesn't work. Okay, so this is the experimental conclusion. So now, what should we conclude about that? We should say, okay, that's fine. So I will try to pull the rope. And so the first idea is, let us ask to Einstein, Podolsky, and Rosen what they think about that. They are dead, so difficult to ask, but actually they wrote it in the paper, in their paper. So if you look at this very famous paper, 35 paper, so you know that EPR idea is that if you have two separated systems, if you measure some Q1 on the first one, you can deduce Q2 on the other one. If you measure P1, you can deduce P2. So these are momentum and position, but it can be any quantum variable. Then each time you see Q1 gives Q2, P1 gives P2. But Q1 and P1 don't commute for example, position and momentum, so they cannot be simultaneously measured. But so Q2 and P2 cannot be simultaneously predicted. But the idea of EPR is that since particle 2 is very far from particle 1, the value, the real value of Q2 and P2 cannot depend on a remote measurement. So there must be some reality to the value of Q2 and P2 just because particle 2 is far away. And this is, in a nutshell, the basic idea of the EPR reason. So could that not work? Yes, and they wrote it in their paper. This is an extract from the EPR paper. One would not arrive at our conclusion that quantum mechanics is incomplete if the value in the quantity P2 and Q2 in the second system cannot be simultaneously predicted, then they cannot be simultaneously real. So you see, it's really based on the idea that the properties of P2 and Q2 are real. So they should not care whether you measure Q1 and P1. This is their basic idea. So this would make the reality of Q2 and P2 depend upon the process of measurement carried on particle 1, which is very far away, so it does not disturb the second system in any way. And then they write, no reasonable definition of reality could be expected to permit this. This is the basic idea of EPR. Now, there was Bohr answer, and Bohr was a completely unreasonable guy, because he told this Bohr, it's just an answer with the same title, as you know. EPR criterion contains an ambiguity in the meaning of without in any way disturbing the system. Of course, there is no mechanical disturbance because the system is very far, but there is an influence of the very condition which defines the possible type of prediction regarding the future behavior of the system. So this is a very famous sentence, which is which has a reputation to be completely obscure, but actually I think it's very clear. So, and what I would like is to explain what it means. And so this condition is an inherent element of the description of any phenomenon with which the term physical reality can be attached. So what Bohr says is that there is no mechanical disturbance, no mechanical influence, no influence at all actually. But the real critical point is the very condition which defines the term. And this I would like to come back to that later. So what are these very conditions required by Bohr to speak about the physical reality of quantum physics? So it becomes a little bit philosophical, so you have to do a little bit of philosophy. So when you do philosophy, you have to tell where you start. Whether you are a complete idealistic or materialist or whatever. So I tell where I stand. So many physicists, including me, support physical realism. So the idea, the purpose of physics is to study the entity of the natural world existing independently from any particle observer's perception and obeying universal and intelligible rules. So I believe in physical reality. So I don't create it in my mind, I observe it. Every of us can observe it, but it's a source of physical realism. So then, obviously, when something is certain and reproducible, you like to tell that it's real. So we like very much this EPR definition. If without in any way disturbing the system, we can predict with certainty the value of a physical quantity, then we want this physical quantity to be real. But we have trouble because it is been test, EPR, blah, blah. Just written like that, it doesn't work. So we have to, again, to don't forget Bohr, the very condition, etc. So can we sort of put all that together? Give a meaning to all these contradictory statements. There is a quotation by Sir Arthur Conan Doyle, you know, Sherlock Holmes. And Sherlock Holmes says, one, you eliminate the impossible, whatever remains, no matter how improbable, must be the truth. Okay, so let's try to make sense of all that. I just go back about physical reality, etc., by comparing classical and quantum realities. So in classical physics, we define systems which are entity of the natural world that can be isolated well enough to carry physical properties. So that mass, so you have particles, you have an ensemble of particles, these are physical systems. Then you can measure the properties of this physical system by using external devices, so you can tell that a particle has a mass, position, velocity, etc. Classical physics. Strictly speaking, you should say when it is measured by this given apparatus. And this given apparatus, all the continuation, I will call it a context. It's what you use to look at your system. But in classical physics, the context, actually, you can forget it. Because once you have the values of the properties of the system, you always assume that these properties belong to the system. So the context is just like an intermediate tool. You will make the measurement and then forget. So once the properties are measured, they are known, they can be measured repeatedly, or their behavior can be predicted. So the properties belong to the system that can identify. Okay, so now let's go quantum. Quantum physics. System, same thing. Is an entity of the natural world that can be isolated well enough to carry properties. Such properties can be measured using external tools that I call a context. Same thing. Once measured, the properties can be measured repeatedly, and the result can be predicted in certainty. They will simply not change. Or you can, if they evolve, you can also compute the evolution in a given context. That is, as long as you know the context. So this is a big difference in the sense that the values of the physical property belong jointly to the system and the context. You cannot forget the measuring tool in quantum physics. It's absolutely essential. And these repeatable properties, we will call it modalities. It's more or less the equivalent of a quantum state, but you will see there are some subtle differences. But it's basically physical properties that you have measured, and you can predict with certainty as long as you don't change the context. So what is real in this approach, at least, is a combination of the context, the system, and the modality. That is one always repeat and repeat that quantum mechanics is a probabilistic theory, which is fully true. But if you just remeasure the same thing, it's not, if you remeasure and measure again the same thing, It's not probabilistic at all. It's fully deterministic. So this is a trick. Using classical language, for instance, the photon has a polarization. In our language, the photon has no polarization. What you can tell about the photon is that it is transmitted with certainty, which is a modality, because through a polarizer oriented at 45 degrees, which is the context. So what is sure is that the photon will go through the polarizer again and again, as long as we don't change the orientation of the polarizer. But the property belongs jointly to the photon and to the polarizer. And this is the main idea. And does that fix the problem? Well, I claim that yes. If you just take the definition of the element of physical reality of Einstein, Podolsky, and Rosen, which is in red, if in any way disturbing the system we can predict with certainty, then there exists an element of physical reality corresponding to this physical quantity. So the only thing you have to add is, without disturbing, never changing the context. So if you don't change the context, the element of physical reality makes perfect sense. But you are not allowed to change the context. So this agrees both with the certainty required by Einstein and also by the very condition. So the very condition of both is what I'm telling, is just that you have to specify the context. And then everything becomes objective again. Obviously later I will change the context. But at this point I can't change it. Then I get certainty and repeatability. So the object carrying the element of physical reality is not a system, it is a system within context. So this is the system, this is the context, you have the observer, everything is embedded in a physical reality. But the object is this thing. In some sense, you have never access to the system except through context. And the object is this combination. So there is this has a consequence that there is a very infamous split or Heisenberg gap, which is this boundary. So this boundary is sort of strange because what is exactly the separation between the system and the context? Actually, it can move a little bit, and it does not really matter for us because the modality is defined in terms of both the system and the context. And what matters is that the system can never include the context. There is always a sort of a screen which allows you to access the system. So it fits well with a very famous statement by Perez and Vrije: quantum mechanics can explain anything, but not everything. Quantum mechanics is a theory of subsystems, which are looked at through context. So now, what makes that it's like that? What prevents to have a unique context where all modalities will be defined? Within a given context, if you make a measurement, you get different possible results, and they are mutually exclusive. That is, this one is true, the other ones are wrong. It's only one result at a time, in a given context. But if you change the context, modalities taken from different contexts are generally non-mutually exclusive or incompatible. If one of them is realized, one cannot tell whether the other one are realized or not. So incompatible modalities are non-classical in the sense that classically you can always specify everything. In quantum mechanics, you specify within the context, and if you change the context, you are sort of lost. This is where quantum probability will enter. So why is it like that? So our basic postulate is a quantization postulate, which is to tell that in a given context, the number of n of mutually exclusive modalities is fixed. It's a property of the quantum system, and it is independent of the quantum. I will give an example later. So this is a little example, a funny example. So just take a polarized photon. So this is a context where you measure vertical and horizontal polarization. So these are two mutually exclusive modalities, and this is another context where you measure these two polarizations. So these two are mutually exclusive, these two are mutually exclusive, but this one and this one are incompatible. So if you are like that, you cannot tell whether you will get this or that. So let's put it classical. I consider this is man and woman, which are orthogonal states, mutually exclusive, more or less. And smoking and non-smoking, which are also mutually exclusive properties. So classically, you would have four cases: smoking man, smoking woman, non-smoking man, non-smoking woman, okay, which are mutually exclusive, classically. So I start from context plus this one, I select woman, which are these. Then I move to this context, and I have a random result, but I select smoking. So classically, it should be smoking women. Really very important. These were women. Now I select smoking, so these are smoking women. Now I go back to the initial context, and then with some non-zero probability, I get this. But this is man. So this shows clearly that half of smoking women are actually men. This is a clear proof. So why nonsense? Because smoking and women are non-exclusive modalities. They cannot be combined. So here I'm doing something which is forbidden by my formalism. My n, the number of mutually exclusive modalities is 2. So 2 is okay for man and woman, is okay for smoking and non-smoking, but here I try to make 4. And so this contradicts the formalism. So you see, in quantum mechanics, you cannot combine, you cannot get more details in some sense. If you have man and woman or smoking, and these are just images, but it's just to explain that this, if you bound the number of mutually exclusive modality to 2, you simply cannot define 4. So this is perfectly meaningful classically, and it's perfectly forbidden in a quantum realm. So again, this is the same thing for photons. So now what I tell is that if you agree with that, then you are stuck to use probabilities. Otherwise, you get to contradiction. So if you have two systems, then let's give the example. So if I go back to my polarized photon, I have two mutually exclusive modalities, vertical or horizontal. Diagonal, I have the two other ones. So these are okay, these are okay. But if I combine the result, this is a smoking woman story, I get this thing, and it's forbidden, because then if this was true, I would have 4 modalities, which is excluded by my postulate. So then, what can I do? I am stuck. The only way to proceed is to use probabilities. So the only relevant question that can be answered by the theory is, if the initial modality is B in context C, what is the probability to obtain B prime in context C? If I would obtain more than that, I would violate the initial postulate that n equal to. Obviously, I can have systems with n equal 4, but they are different quantum systems. And so the fact that you are stuck to 2 results in any context, or n results in any context, is extremely powerful. And actually, what we tell is that this is a result for the quantum formalism, as we will show later. So here you see probabilities are not related to any ignorance. There is no hidden variable, nothing like that. It's the ontology of the theory, which tells that there is no global context where all modalities can be meant theoretically. In classical physics, there is a global context. Actually, there is only one context, so this doesn't matter. But in quantum mechanics, it doesn't work this way. Okay, so this is basic idea. And I want to give some example of using it. As you say, we see it works pretty well. So let's start again with Bell theorem. So we have again the 2 polarized photons, we make measurement, get plus or minus, you know all that. You have some random distribution, then you calculate a correlation function, which is the average product of the result, which are plus or minus 1, and then you get these famous Bell's inequalities, which is validated by quantum mechanics, and quantum mechanics wins after 30 years of efforts. So how can we explain that in my formalism? So I have Alice and Bob, which will exchange photons. They will exchange an entangled pair of photons. Now we have 4. For 2 photons or 2 spins, I have 4 mutually exclusive modalities. So in this context, which is a global context, I can define an entangled state. And I have 1 modality among 4. So typically the 4 mutually exclusive modality are the 4 Bell states. But I take one of them, for instance, a single state, and then Alice and Bob will make measurement of that. Now, if Alice makes a measurement in her context, and Bob also in his context, since 4 mutually exclusive modalities, which are plus or minus here and plus or minus here, which is 4 mutually exclusive modalities, but they are not exclusive with these ones. So now it's 4 instead of 2, but it's exactly the same story as a smoking woman. But now here I have 4 situations, and here I have 4 incompatible results. So now if Alice makes a measurement, she gets a result. She knows that there was initially an entangled state, so she can predict with certainty what will happen at Bob's. But what she can predict actually is what will happen for Bob's system in her context. Because she does not know Bob's context. Bob is very far away. So you see, the trick is that after measuring on one side by Alice, what happens on Bob's side? There is no influence at a distance at all. Nothing happens on Bob's state. But Alice has a context and Bob has a system, and both are needed to define the modality. So actually the context, Alice has it's a prediction, it's a modality for system 2 and context 1. So if you want to check it, you have to put them back together, and then this can be done only in their common future. There is nothing instantaneous, but there is a modality with split context and system. There is ghostly action at a distance, not at all. The new modality is defined locally at Alice's side, knowing the initial antagonism. And here the context and the system are in different places. Bob can do the same, then he will get a different modality, because it will get a modality for Alice's systems in his context. So are there two different realities? No, because modality is a certainty in a given context. And in different contexts, if they measure different things, they will have the same probabilistic relation as before. So everything is nice. And actually, there is quantum non-locality, but quantum non-locality results from the composite nature system of plus context of the quantum nature. So you see, it gives there is, some people then know there is no quantum, there is no non-locality. I tell there is non-locality. But non-locality, quantum non-locality, has nothing to do with any influence or action at any time. So when Alice measures something, nothing happens at Bob's side. But there is a new modality which is defined in a new context, and you can check it later if you want. Modality means that if you combine, for instance, Alice's context and Bob's system by bringing them together, you can predict something with certainty because it's a modality. So you can write some equations. I will skip the question, but you may ask later if you're interested, just to show that what I just told with equations contradicts Bell's hypothesis. Obviously, since I agree with quantum mechanics, I have to contradict Bell's hypothesis. I skip that, but I may come back later if you have questions. Okay, so now can we reconstruct the quantum formalism from these ideas? So let's try to do it. So we know that we have to use probabilities. So what is the question we can ask? We can ask, so we are in a given context, we have some modalities. Another context, we have other modalities, always the same number. And so what we want is probabilities, it's a matrix, n by n matrix probability, connecting this modality in this context and that modality in this context. And what you know, it's an n by n matrix. You know also that if you start from here, for instance, you have to reach one of these. So all the lines sum to 1, and such a matrix is called the stochastic matrix. So now, a general stochastic matrix is very general. It can be classical, it can be quantum. The specificity of quantum mechanics is that this matrix for quantum mechanics is not only stochastic, it is unistochastic, which means that all these probabilities are modulus square of the unitary matrix. And if you can show that, you get the quantum formalism. So I will try to show it. So just recapitulate the axioms. So there are modalities. So modalities is a certain unrepeatable probability attributed to a system and a context. The value of n, that is the number of mutually exclusive modality, is a property of a given quantum system and is the same in all contexts. This is the basic stuff. You can change context. So it's, in my case, it's important to be able to change continuously context when you have polarizer or stem like magnet, you rotate them continuously. So they are classical objects, so they are related between continuous transformation, and it makes a group, there is a group of change which correspond to changing the context. So by definition, modalities cannot show up independently of a context, but there is a very crucial issue that the same physical property may have the same value in different contexts, with the same condition of repeatability and certainty. It means that in some sense, if you know a modality, you can recover it in another context, with certainty. So in classical physics, there is only one context, so it's always the case. If you know something, it's valid in any context, since there is only one context. You may imagine a fully contextual theory, where in each new context, you go to a completely different universe. That is not the case either. In quantum physics, this is partly the case. That is certainly can be transferred between contexts, and we call that extra-contextuality. There is big debate, is it contextual or non-contextual? So we just throw it away, and then it's extra-contextual, and we explain that. And this is very important. Yes, just if you know, just to tell you where I am going is to Gleason's theorem. So if you know Gleason's theorem, keep in mind that I'm going to Gleason's theorem at the end. But I sort of set the scene to use Gleason's theorem at the end. So for instance, if you take 4 optical fibers with 1 photon, this is the context, and the modality is that the photon is in one of the fibers. So it's a 1 photon in an n transmission line, so it's a QD to be equal 1. So this is contextual. If I mix the fibers, I get a new context by permutation, for example, but you see that certainty is transferred from this one to this one. If it is here, it's just a permutation, so I find it there. So here I can make more complicated transmission, put beam splitter, but you see this one is, so each time it's a new context, but I can follow this modality. And following the modality is just what I call extra-contextuality. And so this is very powerful also. That is, it can be turned into a rule. The certainty of a modality can be transferred between contexts corresponding to the same physical quantity measured by different ways. So this transfer is an equivalence relation for modality. So we call it extra balance. So it's extra contextuality, and the property which relates this and this modality, we call it extra balance. Keep in mind that I have Gleason's theorem as a goal. So another very famous example is 2 spins. So for instance, for 2 spins, you can measure the spins separately, and then you get the famous result plus, minus, minus, plus, minus, minus. You can also measure the total spin, and then you get this S equal 0 or 1, and if S equal 1, you have 4 n values, so there are these 4 states. It's the same system, so it's always 4 states. It's my basic theorem. I can also make bend measurement, and then I get these 4 states. And now where is extra balance in there? It is simply that actually these 2 modalities are extra balance. That is, if you know that you have plus with separated measurement, you are for sure, you know for sure that you have S equal 1, n equal 1 if you measure the total spin. Same here, these 2 are extra balance, but these 2 are incompatible. But here you see there are different contexts with extra balance modalities. And same thing, if your total spin is here, you know for sure that it's psi plus. And if it is 0, 0, this is the famous singlet state, you go for sure that it is that state. But these 3 contexts are different. They are really different. They are related probabilistically, but not completely, because you can always transfer certainty between contexts. So this is a rule. The certainty of a modality can be transferred between different contexts, and this transfer is an equivalence relation. So if you know Gleason's theorem, you should guess where I am going, but I will go, even if you don't know it, you will see it at the end. So then, given the modality, the probability to get another possible modality depends only on the extra balance class. Because if you are transferred by certainty, you have certainties. And it's only when you change extra balance class that you get a probability. So the probability will depend only on the 2 mathematical objects associated with 2 extra balance class. So the mathematical object, which will be a psi, you don't associate it with a modality, but with an extra balance class of modalities. So then, the element of any stochastic matrix, yes, so this is a lemma, you can show that. This is another lemma, is that this conditional probability for any stochastic matrix can always be written like that. It's quantum classical, so it's a product, it's a trace of a product of projectors, but with 2 matrices here, R, the same matrix, which is a positive diagonal matrix with these conditions. So this is very general. This is classical quantum, it's always so you can always associate projectors with extra balance classes. You don't get quantum mechanics, actually, yet, because these are, you see, what should I get to get quantum mechanics? If R is identity, I get both through. But here, since it's general, R is just such a matrix with these conditions, but you have no quantum mechanics yet. So what is the missing step now? Well, that's Gleason's theorem. So sorry. I'm sorry, I'm missing a slide here, which is an important slide. Let's try to see okay. So apparently I made some strings, and so one slide vanished. But I can tell it. So now, what you can look at what I've written here, and what I want to know is to calculate these probabilities, and I know that according to this simple lemma, the probability to get any other possibility in any modality depends only on the extravalence class, and also I have a stochastic matrix, all probabilities to end up somewhere, sum to 1. So if I just use that, these are the hypotheses of Gleason's theorem, which is a very famous theorem from 1957, my birthday, by the way. The Gleason theorem tells you that if you have all these conditions, all the conditions that I have introduced, then this R is 1. And then you are done. You get the Bond's rule, and you can associate projectors to equivalence class of modalities, and you get the quantum formalism. So you see, so Gleason's theorem is very, there is a missing slide, but Gleason's theorem is very famous, and it has been used to demonstrate Bond's rule in the framework of quantum logic, for instance, you know that very well. Now, I don't want to use quantum logic. I use only physical argument, and so I build up physical argument so that I get Gleason's hypothesis. And from Gleason's hypothesis, I get the quantum formalism. And I think it works pretty well. So I told that to many people, but there is an obstacle, which is that physicists don't like Gleason's theorem. So why is it so? For instance, there are many recent papers about getting Bond's rule, reconstructing quantum formalism by Surek, Massanes, Camelo. They all start by telling that Gleason's theorem is bad. I disagree with them. I think Gleason's theorem is fantastic. So, what are the usual criticisms? They say that Gleason's hypotheses are too strong because you associate projectors with measurement result, and then you assume that the probability depends only on the projector, but not on the context in which it is embedded. This is a basic Gleason's hypothesis. So is it strong? No, it's not strong. This is just what I explained to you before. All my stuff is built and to get that, basically. Because the probability depends only on the projector, because the projector is associated to an extravalence class. So the extravalence class, by definition, goes from context. So I'm fine. So the answer is that associating projector to physical events or modalities can be done without restriction of generality. You don't have to assume anything because you have this little lemma. The actual hypothesis is what people call non-contextual assignment of probabilities. You have to assign a probability to a projector, whatever the context. This is very strong because if you assume that, you get Gleason's theorem and then you get Bond's rule. But this non-contextual assignment of probabilities is just a consequence of what I have told before. So there is a perfect physical fit with the CSM framework. So I'm very happy with Gleason's theorem because I get quantum mechanics from it. And I sort of prepare the ground for Gleason's theorem. So another big criticism against Gleason's theorem is that it's too complicated. It's a 30-page demonstration, which is really tough, I must say. It's very, very simple. So it's maybe I think I more or less understand it properly. It really took me some effort. So it is complicated because these hypotheses, these are the hypotheses. So it's just almost nothing. So it's absolutely fantastic that you can deduce Bond's rule from that. But there is no other choice. You can't deduce Bond's rule from that. So it's really, really good. There are all kinds of Aristotle C's. So this article in 57 is really difficult. Yes, there is another paper which was written in 85 by these guys who are mathematicians, which is called an elementary proof of Gleason's theorem, which should be accessible to any student with master degree in mathematics. They say, well, this is really nice, and this I can follow. But But this is really beautiful. If you write a little bit mathematics, it's absolutely fantastic. Anyway, here's the result. So you get Bond's rule at the end, and so my physical framework get you at the end to the possibility of using the differential theory. So maybe the last slide. So it's about this quantum omelette. I think the quantum omelette was used by many people. This is, I think it's from E.T. James. It has been used by Christian Devol, by Carl. Did you use it? Yes. Rob Strickens also. So my version of unscrambling the quantum omelette is simply unscrambling physics from mathematics. That is, a modality is a physical phenomenon involving a system and a context, and then it's sort of matched to what we call psi. Usually, psi is a state vector or projector anti-state vector, which is a mathematical object associated with a class of equivalent modalities. So my take on that is that if you really separate the physical thing and the mathematical representation of this thing, you unscramble a lot of things. I'm not sure everybody will agree on that. So clearly this is also related to Bohr's view. CSM is close to Bohr's view, but for CSM the explanation of quantum behavior is quantization. So for instance, Rovelli Zeilinger said Bohr never really insisted strongly on quantization. He insisted on complementarity and things like that. But I don't speak about complementarity at all. So contextual quantization, which is our main hypothesis, implies that modality are related probabilistically between contexts. Modality are neither contextual nor non-contextual. Non-contextual would be classical, contextual would be bizarre, but they are extra-contextual. You have to mix up context throughout modalities which are transferred with modality. And then the psi is a mathematical way to calculate this probability. It's a probability theory. So I don't, for instance, the standard question is psi real? So for me, it makes no sense. Psi is a mathematical object, and what is real is the modality, which is a physical problem. Okay, well, so that's the end. So these are my colleagues, Alexia Auffeves and Philippe, who is a philosopher, and we discussed a lot about reality, etc. So this is sort of a proposal to unscramble the omelette. Now you may like it or not. Anyway, thank you for your attention.
Thank you very much, Professor Philippe. And you made it very quick, so we actually get back to our schedule. Almost back on our schedule. So we have, I guess, a few questions. Whoever has a question, now it's the time to ask Professor Grangier. So raise your hand, and I'll go, because since we are streaming this lecture, the question has to go on the microphone. So,
thank you. Thank you for the talk. Very interesting. Will it be possible to define an experiment to check Gleason's theorem?
Gleason's theorem gives you Born's rule. So Born's rule is maybe the most verified part of quantum mechanics so far. So there is, I don't, all quantum mechanics is based on Born's rule. So the basic question that people ask usually is, where does Born's rule come from? And so what I tell is that, so it's well known also that Gleason theorem implies Born's rule. It has been used by quantum logic by many people. The big issue, which was the main point in my discussion, is where do the Gleason's hypotheses come from? And since they are a little bit tricky, there are many papers telling that they are irrelevant, or that they are too strong, or they are sick, or that so my point is that no, this Gleason hypothesis really corresponds to the physical behavior of quantum systems. And if you ask me that, then everything follows. You get Born's rule, you get Philippe's transformation. I can give more details on that also. And so, in some sense, yes, okay. Do I answer your question? Now, doing an experiment would be checking quantum mechanics, but this has been done for almost 1 century now.
Any other question? Raise your hand so I know How many questions do we have to handle? One more? No more? Okay.
I have just two remarks and one question. The first remark is that in my understanding, Gleason's theorem starts with the assumption that within co-measurable propositions you have classical probabilities. The classical Kolmogorov axioms, classical probability theory are satisfied, and if you paste all these classical contexts together, there is one and only one type of probabilities, and these are the quantum probabilities.
Yes.
Now, Gleason's theorem, as you certainly know, this was stimulated by McKee in their discussion, and McKee brought this up because Birkhoff and von Neumann introduced quantum logic, this famous quantum logic paper, which was based not only on Birkhoff's latest theory, but on von Neumann's Hilbert space theory, which again was based on Dirac's suggestion of the Hilbert space. So for me, the understanding is that really Gleason's theorem is intimately tied to the assumption of the Hilbert space, and so you need vectors, and once you employ Gleason's theorem, you would need, I believe, vectors. So this is my question. If I push you a little bit, I would say putting in vectors in Hilbert space and regaining quantum mechanics wouldn't surprise me too much. I also love Gleason's theorem, and we are very close, but this I would say it's just consistent.
This is this lemma in some sense. That is, if you have a stochastic matrix can be anything except stochastic. So you can write it this way. And so you see here you have all the ingredients of the Hilbert space. You have, for each context, you have a set of orthogonal projectors, so this is a Kolmogorov probability in each context, so it's the same that we have. So probabilities are classical given the context, but the strength is when you change context. And so this is just a mathematical identity. It doesn't tell you anything about quantum, but now you have these projectors. And so if you think a little bit about that, we did that in one of our papers, it's really sort of natural to associate projectors with extravalent classes. And then set of orthogonal projectors are associated with context. I think we say just the same thing in your course.
I think we entirely agree. The only thing we probably don't agree is the necessity that it's necessary and sufficient.
Yes, no, so I discussed that with mathematicians. So can I prove that it's the only possible way to do it? So mathematician told me, no way, you will never be able to do that.
This is my
But now there is part of heuristic in that. So what I tell is that if I put projectors, actually I don't get quantum mechanics, because as long as R is not identity, it's not quantum mechanics, it's just something general. So why do I do that? I do that because it allows me to go one step further, which is to associate projectors with extravalent classes. And once I do that, I'm done.
Okay, and just with regards to Gleason's theorem and the complications of its derivation, and I know that you mentioned that many people try to derive it in a simple fashion.
Yes.
And of course, Bell, this is and also Pitowski has many papers on trying to do this. Now, if you read Gleason's paper, the second chapter, the second paragraph, contains a beautiful construction based on Pythagorean theorem, but this only applies to pure states. So if you read nothing, you should read this.
Sure, but I know that, yes. And actually, when we use Gleason theorem in our we apply it for pure state. For pure state, yes, it's a framework that you reach the probability 0 and 1.
It's just the Pythagorean property and the square.
It's so-called Pythagorean lemma, so it's really, really nice.
So if you don't need mixed non-pure states and just rely with pure states. It's just easy because it's Pythagoras. And
well,
it's in the second paragraph. It's better. And one issue comes up to me, which we are friends in a certain sense, because I had a recent discussion with Andrew Siemens about the following issue. And you were saying this also. You were saying that we can operationally define one context. And one context, or one modality, and that's it. Now Siemens, I recently wrote a paper for the Pitowski volume, and Siemens had the following critique. He said, well, if you have one pure state prepared in a 3D system, or from 3D on, you have all the orthogonality contexts defined by way of, for instance, the Pitowski uncertainty theorem. So you have a continuity of contexts which are value definite.
Yes.
But I also tend to agree that as you make only one experiment, you are fixed to one context. But
yes.
I would like to know your opinion on the Siemens argument.
So I don't know very well this argument. What I know very well is that the basic, the core of Bison's theorem is just this idea. If you get this one fixed, you can rotate like that.
Yes, and if this is true, then all the others are, then the entire star-shaped Greek terms are value.
So it's my third axiom. The third axiom is that you can move continuously among contexts. And moving continuously among contexts is just doing that. And this is absolutely essential for Bison's theorem. If you just look for pure state, actually, you just need three-dimensional pure space. You do this trick, and then you, after some effort, you get the result. So for me, I have no problem. I don't see the problem actually. I know where of this thing.
No, the problem is that if you state only one context,
yes,
value definite. This gives you that if you assume that this is true, then a continuity of context is value definite.
It's essential, yes. No, I agree. If you have only one context, you don't go very far because it's basically just you have just probabilities in one context. But in order to get anything along these lines, you must be able to change context. So the big question is, is it needing to change it continuously or is discrete enough? So I had a big fight with Cabello about that because with his graphs he thinks that discrete is enough, but for reasons you need continuity. And actually, Bison's demonstrates continuity. And it's a mathematical question I cannot solve. Is there an equivalent, I don't know, maybe you have an equivalent, is there an equivalent of Bison's theorem if you have a non-continuous context? And so basically Cabello tells yes. I'm not so sure, but why not?
There's a paper that's called the nullification of the Cauchy-Becker theorem. And in this says that if you have non-continuity but denseness, you get an entirely different probability.
Okay. So we may discuss that later.
Okay, we have time for one more question, and then
sorry, it gets a little bit
make a little announcement.
Very short one. I got the impression, I'm absolutely fine with Bison's theorem, but I don't see how this can be used in order to go towards positive operator Bennett measure, so more general measure. And the whole structure you presented somehow seems to me that it's not easy to generalize it when you don't have orthogonal projectors, when you don't have projectors at all.
You just ignore part of the information. And my view of POEMs is actually it's PDM where you ignore some part of it. It's like density matrices.
So we don't agree on that, but it's okay.
It's the same thing for density. With Bison's theorem, I use it with pure states, but then I automatically get density matrices. Bison's theorem actually gives density matrices, and to get my work. Since I'm concentrated on pure states here, I use some restriction of measurement to be restriction of states to pure states.
POEM are not just because you speak about density matrices. I mean, the kind of operators you use to describe the measurements are different. They are not orthogonal. They are class operators.
Oh, you agree with me that there is a theorem that any POEM is a PVM where you ignore part of the information or part of the stuff?
Not mathematically.
Okay, so we can discuss that again.
Okay.
But this is my view of PVM. POEM with respect to PVM is a little bit like density matrices with respect to pure sets. No, you don't agree with that? Okay. Do you agree now?
So thank you, Professor Grangier. One more time.